Hello and welcome. I'm Pravir, and today's session is Enhancing Abstraction in Large Language Models through Nature-Inspired Semantic Patterns. Now, in this session, I'll cover the gist of this paper, which is the same name. I'll very briefly cover some of the other approaches to enhancing abstraction in large language models. But then I'll get to the heart of the matter, which is really looking at an underlying algorithm of fourfoldness, translate that into an equivalent algorithm for language, suggest potential transformer modifications, and then the chosen modification of changing the weighted scheme for the Q, K, and V vectors. I'll briefly summarize a use case, and then I'll conclude. The gist of this paper is the following. It's based on the hypothesis that there is a fractal pattern that organizes the structure of matter and life. Now, if this is the case, then language, being a reflection of reality, must also be organized by this pattern at a subtle level. I'll refer to this fourfold pattern as KNPOPRH, which correlates with roughly with concepts of knowledge, presence, power, and harmony. And then the gist is that by incorporating these elements into the transformer architecture of LLMs, specifically by enhancing self-attention mechanism through additional QKV weights, the nuanced understanding and generation of text can be enhanced. So when we look at abstraction in large language models, there's several things that have been done already. There's structured world knowledge from knowledge graphs that's incorporated in pre-training process in tools such as ERNIE 3.0. There's integration of knowledge during the fine-tuning phase, leveraging common sense knowledge bases such as Atomic in approaches such as Comet. There's the capturing of complex relationships within the text using attention mechanisms to weigh the nodes of a graph, such as in the graph attention networks approach. There's large-scale data sets to enhance a model's understanding of everyday common sense reasoning in the data set such as Atomic. And then there's ambiguous pronoun resolution that is basically used as a test to advance levels of common sense reasoning in approaches such as Winogrand. Now, in the approach that I'm going to focus on today, it's based on an algorithm of fourfoldness. And what you see here on the left-hand side is basically a generator of different mathematical spaces. So I'm going to walk us through this in a little bit of detail. And this generation of mathematical spaces is initiated by imagining light to travel differently. So if we imagine light, which of course we know in vacuum travels at 186,000 miles per second, if we imagine this traveling infinitely fast, and then we conceptualize the volume can be of any size. And if we have that light source at the center, that where the light is going to travel infinitely fast, then it's going to instantaneously fill up the whole volume. And so it's going to have a property of presence in that whole volume instantaneously. If anything not of the nature of light were to arise, it would be overpowered by light sooner or later. And so there's a property of power. Since everything that appears or disappears in this volume is going to happen in the fabric of light, light's going to have an instantaneous knowledge of everything that's happening in that volume. And so there's a property of knowledge. And since everything is happening implicitly in the nature of light, there's going to be a property of harmony. Now, through an act of quantization, and what do we mean by quantization? Quantization means that these abstract properties, when we quantize them, they become more discrete or definitive. And this process of quantization is imagined to occur when light projects itself at a slower speed, less than infinity, but still a constant speed. And that's what's depicted by the second line here. So when this projection or quantization occurs, then what's contained within these conceptual spaces of PR, PO, K, and H becomes four sets of PR, a set of PO, a set of K, and a set of H that can be envisioned as having a large number of elements, all related to the concept of presence, power, knowledge, harmony, respectively. Through another act of quantization, we can imagine a further differentiation taking place where an infinite number of seeds are created, and these seeds are unique combinations of elements from these four sets. And that's what's depicted by this line here. So what we've ended up with in this mathematical space is a large number of unique subtle seeds. Now, when light is projected in this thought experiment to the known speed of 186,000 miles per second, then there's several things that are happening simultaneously. So first of all, this layer of subtle seeds becomes more granular and becomes a substance of space. The seeds, these subtle seeds, over a course of time, will display the subtlety in more material form. So that's envisioned by this process that we know as time. The transformation from the subtle to the more material is an energetic transformation. And so we conceptualize this notion of energy. And as we know, when we look at any kind of seeds around us, or the way matter has formed around us, it happens in various collectivities. And so this reflects this idea of gravity. When we look at space-time energy gravity a little more deeply, we see that space is nothing other than a symmetrical face of this concept of knowledge, because what we have is an archetype of all possibilities spread through space. Time is a symmetrical face of this concept of power, because through the process of time, against any obstacle, that which is contained in the seed will materialize. Energy is a symmetrical face of presence, because that which is subtle becomes material. And gravity is a symmetrical face of harmony, because there's always a collectivity. So we see that this underlying algorithm of fourfoldness creates a first known set of elements that defines the cosmic parameters of space, and we call those parameters space-time, energy, gravity. When we iterate this algorithm further, it will create the layers of matter and life. We know, for instance, that all quantum particles are arranged in a set of 4 particles in a standard model: quarks, leptons, bosons, Higgs boson. We know that all known atoms belong to either the S group, P group, F group, and D group. Again, there's a structure of 4. And when we look at molecular plans that animate any living cell, we know that there are only 4 molecular plans: lipids, polysaccharides, proteins, and nucleic acids. And just to show that there's still this implicit harmony, or rather symmetry, that's being maintained, I'll just take the example of the molecular plans in cells. When we think about the essence of what a nucleic acid stands for, then we can say that it's a carrier of knowledge, because we know that the nucleic acids will basically create DNA, which creates libraries in cells, which houses the knowledge that a cell imparts to future generations of cells, and also that creates a blueprint for how all the components of the cells are going to act. We know that polysaccharides are chains of sugar that provide energy and power for the large activity within a cell. We know that proteins, for example, when we look at the human cell, there are over 30,000 different proteins, are ubiquitous across the cell and involved in all kinds of activities. So it's a symmetrical face of presence. And we know that lipids create natural compartments in cells, and this allows work specialization and harmony, and therefore can also be seen as a symmetrical face of harmony. The point being that when we look at this very first layer of space-time energy gravity, and then a far more complex layer of polysaccharides, lipids, proteins, and nucleic acids that form the molecular plans in cells, then we also see this symmetrical face. So the takeaway from this slide is that this algorithm is generating fourfold structure across many different levels. And there's several books that I've written and many different articles for IEEE and Springer Nature that elaborate this process in more detail, and also go all the way up to human collectivities and civilizations and economies, and show that these are also structures that are basically precipitated by this symmetrical fourfoldness that shows itself at many, many different levels. Well, if that's the case, then all language, which is a reflection of reality and is a way by which we maneuver through reality, must also be organized by such fourfoldness. And so that's the key hypothesis in this paper and in this presentation. And if we now, based on this algorithm, try to create an algorithm for fourfoldness in language, then we can assume that in any complex text, no matter what the text is, there would be special elements, or there would be elements that belong to these four primary sets, which have a large number of elements in them. We can refer to these sets as PR, PO, KH, and here the plus sign designates that these are the positive primary drivers in that complex text. And this set of sets is referred to as CS plus. Now, in the algorithm for language, it would be important to understand the balance between PR plus, PO plus, K plus, and H plus, because the fact is that in any surfacing organization, whether it's material or whether it's language, has to do with language, there's going to be a focus, an implicit focus, that is accompanied by other kinds of secondary drivers. So it becomes important to understand what's leading in that complex text. The primary drivers in that complex text that's leading in that complex text are referred to as prime plus. The secondary drivers that basically support the primary drivers are called secundus plus. And it's also important to understand this concept of enrich, which refers to how secundus plus enriches prime plus. And then on the flip side, it's important to understand all the marginalizing elements in that complex text as well. And we can refer to these elements as belonging to four sets that we call PR minus, PO minus, K minus, and H minus. And similarly, we can designate prime minus and secundus minus as the primary negative drivers and the supporting negative drivers. And when we want to analyze any complex text, we can do it in the following way. So this becomes the algorithm for interpreting any complex text, no matter what kind of text it is, whether it's literature, whether it's an economic analysis, whether it's a theory based on scientific data. We want to first establish the balance between prime plus and prime minus. You want to understand the overall balance, CSBL. We want to understand the enrichment that secundus plus is, by which secundus plus is an enhancing prime plus. We want to understand the overall milieu in that text by understanding the balance between CS plus and CS minus. And we also want to understand the primary drivers of marginalization in that complex text as captured by prime minus and secundus minus. Now, the question is, when we think about the transformer architecture, what kind of modifications could potentially support this algorithm that must exist in language and any other complex text? So there's the approach of semantic tagging, and this refers to a process of enriching data with metadata. On the positive side, basically, this becomes a pretty rigorous process, meaning that we can tag elements of CS plus and CS minus that would then semantically allow for analysis of different complex texts based on this scheme of metadata. On the flip side, the effectiveness of semantic tagging depends on accuracy and consistency in the tagging process, which has its own challenges. We can also, within the transformer architecture, put in some additional layering. And this, as we know, the more the layers, the more the possibility of abstraction it allows. So on the positive side, more layers can potentially lead to more nuanced understanding of the complex interactions between elements within the CS plus, CS minus of that complex text. On the negative side, it's also known that additional layers, especially if a data set or a model is already large, may only offer marginal improvements. There's also the process of embedding extensions, which are numerical vector representations. And this has to do with capturing more complex relationships, building on implicit representations made through statistical patterns in the data. So rather than, for example, trying to get a statistical data point between a pair of words in text, what this could do is provide the relationship between triplets simultaneously or quadruplets and so on. So on the positive side, embedding extensions may allow for more targeted information retrieval by extending the embeddings, which are these numerical vector representations, which would allow deeper understanding of how these elements interact within the text. On the flip side, what this means is that there's a much higher training complexity, and also there's a risk of overfitting the data. Our intuition, however, is that the easiest way to go about transforming the transformer architecture or modifying it is by creating additional weights to the QKV vectors. And if intuitively, why this makes sense is because if this fourfold algorithm is natural in any text, then the additional weights should be able to capture this multifaceted view just organically. And whereas the other modifications require a complexification in the overall model, this or more layers added to the model. Here, what it means is that just by adding certain weight vectors, that these kinds of relationships may be grasped naturally in the text. The con of this approach is that incorrectly balanced weights may introduce biases in certain elements, but there's also ways to minimize this. So basically what this boils down to, if we take this approach, then we have the input that's represented by X, and that input, as we know, is projected into three vectors, the query, key, and value vectors. But what we're suggesting is that now we have additional vectors that correspond to each of the 8 sets that had been introduced in the algorithm, the PR plus, PO plus, K plus, H plus, PR minus, PO minus, K minus, H minus, and that the vector for the queries basically now is constituted by this form that you see over here, and similarly, the vector for the keys and the values. Potentially, this could increase the expressiveness of the model because we are looking at the same tokens or words from multiple abstract perspectives simultaneously. The computational complexity would remain on the same order. So in the original mechanism of the transformer architecture as is, it's a quadratic complexity that exists. And with the extended weight scheme, it would still remain quadratic, but there would be additional matrix additions and multiplications that would increase the complexity by some degree. One of the risks of this approach is that because of the additional weight vectors, we have eight additional weight vectors. The risk of gradient vanishing or exploding is going to go up. And so this will need to be managed very carefully. Now, I want to draw attention to a use case, a particular use case. But first, I'll just mention that the intuition is that there would, in general, be more depth to analysis in a diverse set of use cases that may range from literature reviews to economic analyses to social sciences to medical diagnostics to in-depth scientific research. Of course, this will have to be tested. But based on something that I've done in the past, I want to draw attention to a particular use case. In between the years 2008 to 2015, I wrote a series of 3 books on fractals. The first book laid out a theoretical way to look at organizations, and the theory was essentially based on a fractal representation of the 4 properties that I've introduced here: presence, power, knowledge, harmony, PR, PO, K, and H. And so that entire theory is driven off an understanding of these 4 drivers. And the second book analyzed the global financial crisis between 2008 and 2009, the global crisis that occurred at that time, and also was based on the interpreted play of presence, power, knowledge, harmony. So basically looking at looking at financial data trends from the point of view of these fundamental drivers that were fractal representations of presence, power, knowledge, and harmony, there was a different order of analysis and recommendations for the development of sustainable society that emerged in that second book. And this becomes a concrete use case for what we would also expect when a large language model becomes capable of seeing this deep pattern, the PRPOKH pattern, and analyzing data based on it. To summarize, the integration of a fourfold natural pattern into LLMs architecture may help in the creation of a more dynamic, context-aware AI system capable of deeper semantic understanding. The architecture's capacity to simultaneously manage multiple perspectives aligned with a subtle fourfold pattern could lead to significant improvements in a range of analytical situations, as I just shared. What's going to be important is that since this is all conceptual, it needs to be tested. So further investigations will need to establish the efficacy of the query key and value vectors and the enhanced weighted schemes. And this could be some kind of baseline. It may become necessary to change the weighted scheme or even to change the model, make it a little more complex by leveraging embedding extensions, semantic tagging, or layering. And this, again, would need to be experimented with based on how the QKV experiments go. And of course, future work will need to look at the scalability of this approach and applicability in a wide range of use cases. It's expected it could be used in literature reviews, scientific evaluations, medical diagnostics, economic analysis. But again, this will all have to be tested out. Thank you.